This section explains the thesis of the first chapter, special relativity and flat spacetime. Carroll separates the stage from the play, the fixed structure of spacetime from the dynamics running on it. He then notes that special relativity is Newton's stage, with one invariant deleted. Newton keeps two invariants. The first is absolute time, a clean slicing of the world into now. The second is absolute time, a clean slicing of the world into now. Special relativity fuses these two into one, the light cone at every event, which alone fixes which trajectories are possible. That is the thesis. The chapter is general relativity, with the hard part switched off, curvature set to 0. You build the geometry of space-time reflex and the tensor machinery on flat ground first, before gravity bends it. Flat space-time is the curvature set to 0, special case that the rest of the book perturbs. This part explains how gravity stops being a force and becomes the shape of space itself. Newton's gravity is a dyad. Matter tells the field how to be, and the field tells matter how to move. General relativity keeps the dyad, but collapses both halves into one object, the curvature of space-time. The move that makes this possible is that gravitational acceleration is universal, the same for every mass, so it can be absorbed into the definition of straight itself. A force felt by everyone identically is really geometry, the shape of the space you are moving through. Free fall becomes unaccelerated motion along a geodesic, the closest thing to a straight line a curved space allows. The ball in flight is more inertial than the one resting on the table. Gravity is not located in space-time. Gravity is space-time. This section explains what a manifold is, built from a single pair of ideas, locally flat, globally free. That pair generates the whole object. Start with the equivalence principle, which says, a freely falling observer sees no gravity. Space-time is indistinguishable from flat Rn in any small enough patch, no matter how sharply it curves at large scale. A manifold is precisely the space that honors this. It is patches that each look like flat Rn, sewn together smoothly, with no constraint on the global shape. That single move buys everything. Curvature can live in how the patches fit together, while calculus still runs cleanly inside each patch. Once you hold the pairing, locally Rn and globally anything, you can predict the boundary cases yourself. A cone fails only where one point refuses to look flat. This part explains why every object falls the same way, and why that single fact removes gravity from the list of forces. Every object carries gravitational charge in exactly the same proportion. Inertial mass equals gravitational mass, so everything falls identically. A charge you cannot vary, one that couples to all matter alike, is not measurable against a neutral background the way electric charge is. You can always step into a freely falling frame where it vanishes locally. A force you can everywhere annul merely by choosing how you move is the arena itself, rather than a field acting on that arena. That is the whole pivot. Universality of freefall, the weak equivalence principle, expels gravity from the catalog of forces and relocates it into the geometry of space-time. The chapter exists to license the manifold. This section explains why a metric alone cannot detect curvature, and what has to be added before curvature becomes a well-posed question. A metric alone cannot tell you whether a space is curved. Flat space, written in an extravagant coordinate system, looks bent. What is missing is a rule for comparing vectors at neighboring points, and that rule is the connection. Once you can transport a vector, curvature reduces to a single question. carry the vector around an infinitesimal loop and check whether it returns unchanged. The failure to return, the non-commutativity of transport, is what the Riemann tensor measures, and it vanishes if and only if the space is genuinely flat. The Christoffel symbol, the covariant derivative, and the geodesic are scaffolding that make that single comparison well defined. The chapter manufactures exactly the machinery that lets gravity is curvature become an equation. This section explains where curvature actually comes from and why the Riemann tensor is the object general relativity computes with. Curvature is not something you read off the metric directly. It is the obstruction to comparing vectors at different points. Differentiating a vector field requires a rule for carrying one vector to another's location, and that rule is the connection. Transport a vector around a closed loop and it returns rotated. That failure to return is curvature, packaged whole in the Riemann tensor, which vanishes if and only if the space is flat. Christoffel symbols, the covariant derivative, geodesics, all of these are downstream of a single move. Comparison at a distance demands a connection, and the metric fixes a unique one. This chapter's labor is converting the intuitive notion of bending into that one structural object the rest of general relativity computes with. This part explains how Chapter 4 turns the geometry assembled earlier into a physical theory of gravity. The naive picture treats gravity as a force. The correct framing is that gravity is the shape of the arena, and the chapter builds the physical theory by demanding that matter and curvature match. The surprise is that the matching equation is not chosen. It is forced. Require a symmetric, second-order, coordinate-free relation between the metric and the energy-momentum tensor. Then impose local energy conservation, meaning the covariant divergence of the energy-momentum tensor is zero. Once you demand that, the Bianchi identity leaves exactly one divergence. Free tensor buildable from curvature, the Einstein tensor. So the equation writes itself. The Einstein tensor equals 8 pi g times the energy momentum tensor. This is the same move that fixes no other currents. Impose the invariances, and the dynamics are whatever survives them. This section explains why Chapter 4 treats gravity as geometry rather than force. Gravity is the geometry of the arena, and the whole chapter descends from a single substitution. Take any law valid in flat space-time, rewrite it tensorially, then assert that it survives the replacement where eta becomes g and the ordinary partial derivative becomes the covariant. Under that swap, the free particle obeying x double dot equals 0 becomes 1 obeying the geodesic equation. It is still undeflected. Only the track it runs along now bends. That is half of Chapter 4's thesis. The other half closes the loop. Matter tells space-time how to curve, and space-time tells matter how to move. The equivalence principle is the hinge here. Gravity's universality, its blindness to what falls, is precisely what licenses recasting it as curvature rather than force. This section explains the Schwarzschild solution, the first exact solution to Einstein's equations. Impose enough symmetry and solving stops being a search. The answer becomes forced. Demands spherical symmetry and vacuum, meaning the Ricci tensor vanishes around a gravitating body and Einstein's equations collapse to a single metric. That metric is Schwarzschild, fixed entirely by one constant, the mass m. The surprise that does the real work here is Birkhoff's theorem. You never had to assume the field was static. Spherical symmetry alone forces time independence. Symmetry here does not merely simplify the answer, it determines it, the way a universal property pins an object to uniqueness. This is the chapter where general relativity first touches the sky, perihelion precession, light bending, and where the black hole already sits latent, waiting at r equals 2 gm. This section explains how symmetry alone forces the shape of spacetime around a mass. Impose enough symmetry, and the field equations stop having choices. Spherical symmetry plus staticity plus vacuum, meaning the Ricci tensor vanishes, collapses the entire space of metrics to exactly 1, carrying a single free number, the mass m. That forcing is Birkhoff's theorem, and it is the chapter's spine. Everything downstream, the orbits, Mercury's precession, the horizon, is reading properties off a solution you never got to pick. Here is the turn that does the work. The apparent catastrophe at r equals 2 gm is a coordinate singularity, an artifact of the chart rather than of the geometry. Only r equals 0 is curvature, real, symmetry as solution, space collapse, and the maps tearing mistaken for a tear in the terrain. This section explains why the whole family of black holes reduces to just 3 numbers. Collapse is a forgetful functor. Throw anything past an event horizon, a star with all its mountains, its infinite tower of multipole moments, and what survives is fixed by exactly 3 numbers: mass, charge, and angular momentum. The no-hair theorem is that projection. The chapter zoo is merely its image, the 3-parameter family. Schwarzschild keeps only the mass. Reissner, Nordstrom adds the charge. Kerr adds the angular momentum. Kerr, Newman carries all 3. Why these and nothing else? They alone are readable from infinity through a Gauss law flux, long-range fields. The horizon cannot swallow. Everything else radiates away. The understated sting waits at the end. What is forgotten looks like erased information, and quantum mechanics forbids erasing it. This section explains why gravitational collapse behaves like a projection, and what the no-hair theorem classifies. Collapse is a projection. A planet's external field needs infinitely many multipole coefficients, and every mountain range leaves its trace. A stationary black hole needs 3: mass, charge, and angular momentum. That is the no-hair theorem, and it is what this chapter is for. Chapter 5 gave 1, Schwarzschild solution parametrized by mass alone. This chapter classifies the whole stationary family, adding charge, giving the Reissner-Nordstrom solution, and spin, giving the Kerr solution. Here is the generative move. Gravitational collapse maps an arbitrarily complex configuration onto a 3-number end state, radiating the rest away. Predict the adjacent case yourself. The parameter count tracks the theory's long-range fields. The infalling matter does not enter it. That erasure is the seed of the information paradox, which Chapter 9 takes up. This section explains how perturbation theory turns Einstein's gravity into a theory of radiation. Drop the exact geometry and keep only its first variation. Write the metric as flat space plus a small h. Discard everything past first order, and Einstein's nonlinear equation collapses into a wave equation. The move is generic. Linearize any nonlinear field theory about a background solution, and you get a linear theory whose free oscillations are its radiation. Here, gravity, stripped to first order, is just a symmetric tensor field propagating on Minkowski space. Its propagating content is 2 transverse traceless polarizations, and their source is the changing quadrupole of mass rather than mass itself. That is the chapter's whole payload. Space-time curvature. Perturbed, radiates. Everything else, the gauge freedom, the detection, the energy loss, is bookkeeping around that one collapse. This section explains how Chapter 7 turns Einstein's gravity into a field theory. Take Einstein's nonlinear geometry and expand it about flat space-time. Write the metric g as eta plus h, with h small. The curvature that was gravity becomes an ordinary symmetric tensor h living on the flat background, obeying a linear wave equation. Gravity stops being geometry and becomes a field like electromagnetism. The chapters whole yield gravitational waves, light bending, and time delay follows from that one demotion. The move is generic. Linearize any nonlinear theory about a known solution and its symmetry, here diffeomorphism, invariance, survives as gauge redundancy in the perturbation. Chapter 7 is where general relativity is made to speak field theory. So, radiation becomes computable. This part explains what symmetry does to the equations of cosmology. Assume the universe looks the same everywhere and in every direction. That is the Copernican principle, cashed out as homogeneity plus isotropy. Once you grant it, something drastic happens. The metric loses almost all its freedom. Maximal symmetry means maximal. Killing vectors and the 10 independent functions of Einstein's equation collapse to a single scalar, the scale factor of t, writing a fixed spatial curvature. That is the chapter's whole move. Symmetry is a dimensional reduction engine, turning the intractable field equations into one ordinary differential equation, Friedmann's, for one function of time. Every later result, redshift, distance, the fate of expansion, is just of t read out. The cosmos reduced to 1 degree of freedom. This section explains how one assumption collapses the whole of cosmology onto a single function. Assume the universe looks the same at every place and in every direction, homogeneity and isotropy, the cosmological principle. Under that assumption, the entire gravitational field collapses to a single number that varies only with time, the scale factor written a of t. That collapse is the chapter's whole engine. Maximal symmetry drains the metric of its infinite freedoms until Einstein's 10 coupled nonlinear equations reduce to the Friedmann equations, ordinary differential equations for one function. The largest object there is gets the simplest description, and not by luck, the symmetry you impose is the compression. Everything downstream, redshift, lensing, the history of expansion, is bookkeeping on that one function. This section explains why the particle concept dissolves once you move from flat space-time to curved. The field is real. The particle is a bookkeeping choice. Quantizing a field means splitting its modes into positive and negative frequency parts. But frequency needs a time coordinate, and curved space-time hands you no canonical one. Different observers slice time differently, so their creation operators mix, and one observer's vacuum is another's populated state. The particle concept loses its absoluteness the moment global time translation symmetry does. That is the chapter's single lever. Remove the flat space. Killing vector that made the vacuum observer independent, and thermality drops out. An accelerated detector reads the empty Minkowski vacuum as a warm bath. Particle number is what a world line's clock resolves, a reading taken by an observer rather than a stock the world holds. This section explains the semi-classical bargain, what you get when you have no theory of quantum gravity but still want quantum fields on a curved space-time. Lacking quantum gravity, you take only the first half of general relativity, matter fields riding a fixed curved background, and you quantize the fields while the metric stays classical. That semi-classical bargain is the whole chapter. It carries a single surprise. This is the one that does the work. Particle number is a property of the observer's mode. Decomposition of a field. It is not a property of the field itself. Fixing a vacuum means splitting the field into positive frequency and negative frequency parts, and that split demands a preferred time. Curved spacetime, or merely an accelerating frame, supplies no such time canonically. So observers disagree on how many quanta are present? From that one asymmetry, everything downstream follows: the Unruh effect, Hawking radiation, the information loss paradox. Empty is empty only relative to who is asking.